Hey, AP Chem. Today we are going to be talking about Dalton's law of partial pressure. And I think that Dalton's law is actually probably the easiest law that you will ever learn in chemistry because if you can add, you can do Dalton's law. So it's not an exceptionally difficult law, but because it is so easy, you are often going to see Dalton's law used and applied with either other gas laws or algebraic manipulations of Dalton's law. So in and of itself, easy peasy. When you add it to other stuff, oftentimes it can be something that gets overlooked. And so we just have to make sure that you're careful that you remember to use it. And I'll show you a couple scenarios that I think you're probably going to potentially see it in. And then we'll do a couple examples, which are, like I said, easy peasy. So if you think about a container that I have here, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Hopefully I count that right. 16 gas particles. And in this container here, we have essentially the same number of gas particles. In the container on the left, it's all one gas, gas A. And in the container on the right, it's 4 different gases, gases A, B, C, and D. And we are going to assume that these are at the same volume and the same temperature. So if we have the same number of particles of a gas in this container, we should, in theory, have the same pressure. And that's the idea behind Dalton's law, is that it doesn't really matter if I have one gas or 10 different gases in a container. They are all going to contribute to the pressure equally. So if I have a mole of carbon dioxide, it's going to contribute to the pressure the same way a mole of oxygen would, or xenon, or sulfur hexafluoride, or whatever we have. It is going to contribute pressure in the same way. And so, Dalton's law is pretty simple. It's that the total pressure inside your container is the sum of the pressures from every gas that's in the container. So in this case, I don't have D on there, but it's like A, B, C, D, all the way to as many gases as could possibly be in the container. And that's literally the law. So if you know the pressure of a bunch of different gases, you could add them all up and get the total pressure. So for example, here we have 5 containers of gases. We've got oxygen, nitrogen, argon, water, and carbon dioxide. If I know all the pressures of each individual one in this mixture, which happens to be air, then all I have to do is add those up and I will get the total pressure. Literally, it's that simple. So if you can add or subtract, you can use Dalton's law. So in this case, since my head here is kind of blocking the pressure of the PSI for the oxygen, we could take all of the values for the 4 gases we do know, add those up, and subtract them from the pressure of the total canister, and we could figure out the pressure that the oxygen is contributing. So there's really basic ideas here. Any gas will contribute the same amount of pressure if it has the same amount of moles, and they all contribute pressure in the same way. So like one gas isn't going to add more pressure just because it's that gas. The only way it would contribute more pressure is because it's actually got more moles of stuff in there. Now, like I said, oftentimes you're going to see a little bit of algebraic manipulation happening here, and that's what you see with Dalton's law. So it is very rare that you are going to see Dalton's law on its own, just as straight up addition. I've seen it once or twice in the exam since I've started teaching it, but it's not super common. So what you do see is actually a manipulation to get us into something called a mole fraction. So what they do is they take the ideal gas law, PV equals nRT, and they solve for P. And the idea is that P equals nRT over V. And if I have, one thing I kind of forgot to mention is that we're taking those gases and putting them all into the same container. So those gases all have the same volume and they all have the same temperature, and then they each contribute their own pressure based on the number of moles that they have. So coming back to this now, if I rearrange my equation for pressure to be the variables that it's equal to nRT over V, what ends up happening is that the R, the T, and the V are the same for each of those gases. So if I would want to take a look at a ratio of the pressure that one gas is contributing and how it contributes compared to the whole pressure, I could set up a ratio where I take pressure of that one part divided by pressure total. But if I do the fancy algebraic manipulation, I'll end up with that gas divided by the total gas moles, and then the R, the T, and the V can cancel out. And so what we end up getting is a ratio where if I take the pressure of one gas and divide it by the total pressure of all the gases in the mixture, that is the same as getting the number of moles at the top and dividing it by how many moles are in there. Now, they aren't the same units necessarily when we put them into that ratio there, but what they do is they give me the same number, okay? So I'm going to get a decimal in this form because if I take pressure divided by pressure, the units of pressure cancel out. And if I take moles divided by moles, they cancel out. But they give me the same thing. And that thing is called a mole fraction. So what a mole fraction is if you have a mixture of different substances and you want to figure out how much one part of the mixture is contributing, what you would do is you would take the moles of that substance and divide it by the total number of moles in the mixture. And that kind of makes sense. Well, what we're getting at here is you can do that and get that same fraction or decimal value by taking the pressure that one gas contributes and dividing it by the total pressure. So that is one scenario where you can apply Dalton's law is through that mole fraction relationship. The other area where you tend to see Dalton's law of partial pressure is when we're talking about collecting a gas with water. And you might say to yourself, why would I do that? But a lot of times, one of the best ways to deal with collecting a gas is by using a water displacement technique, which we will get into in just one second. And then what happens is water is kind of in the mix here a little bit when we talk about gases. So when we talk about water or any liquid, and we've talked about vapor pressure before with intermolecular forces, what vapor pressure is if I have a closed container, it is the pressure of the gas above the liquid at a point where the amount of gas going into the vapor phase, so like up into the gas phase, is equal to the amount of gas that turns back into a liquid. And that's called the equilibrium vapor pressure. So essentially what it is it's the pressure of the liquid the pressure of the gas above your liquid in a closed container. And that vapor pressure is changeable depending on the strength of the intermolecular forces. So if I have strong intermolecular forces, my substance might not have a lot of vapor up here compared to a similar substance that has weaker intermolecular forces at the same temperature. When we take a look at vapor pressure changes depending on the temperature. So this is just for water, and you can see as the temperature goes up, the vapor pressure increases. And hopefully that makes sense to you because as the temperature goes up, the average kinetic energy of those particles goes up. And eventually, if I kind of go back to this picture here, if I have a higher temperature and these particles here have a higher average kinetic energy, some of those particles on the higher average kinetic energy side are going to be able to potentially turn into a gas and turn into a vapor. And the higher the energy, the more they're going to be able to do that. So as the temp goes up, the vapor pressure goes up. Now, as the temperature is increasing, you get to bigger and bigger increases in the vapor pressure until you hit the normal boiling point of water. And if you notice, the normal boiling point of water's vapor pressure is 760 millimeters of mercury. And that is not accidental. That standard pressure that we talk about, our normal boiling point, those two things are linked together. So what ends up happening is that if I have an open container, normally, like I said, some particles can escape because they have a higher than average kinetic energy and they can turn into vapor and they go out. But when we talk about actual bubbles forming of vapor, so evaporation is a surface event that's happening, okay? When we talk about boiling and we actually get a phase change that's happening, that can only really start to happen when the vapor pressure at the top is equal to the atmospheric pressure. So if the pressure of the vapor or the pressure of the escaped particles is high enough, then that water can start to form, since the vapor pressure can be overcome because we're very close to atmospheric pressure. So when we talk about boiling points, the critical part is that the pressure here at the surface needs to be equal to the vapor pressure. Now, if I have a lower than standard pressure, I can boil at a lower temperature. And we see that happening on elevation and like higher elevated areas. Because the atmospheric pressure is lower, it takes less vapor pressure to get to the boiling point. And so you can have your food boil at a lower temperature. And because of that, you are going to need to adjust cooking times and things like that so that you don't run into problems. Now, where vapor pressure comes into play in a lab is that when we do experiments like I had mentioned, where we collect our substance in a liquid or we use water displacement to make that happen, we have to take into account the pressure that water adds to our experiment. And the tool that we use for gas collection is something called a eudiometer. And it's kind of like a burette with a closed end, and then it's like a burette and a test tube, a giant test tube had a baby. And so what ends up happening is that it's graduated kind of upside down like a burette is. And what you do is you put a one hold stopper at the bottom and you fill this up with liquid. Now in this particular experiment, they put acid at the bottom because it's more dense. Then they put a big column of water and then some magnesium. And then what they do is you plug the eudiometer and you invert it into a beaker of water, and then the acid runs down the tube, reacts with the magnesium, and then it turns into a gas. And because the gas is less dense, it's going to go up the tube and you can start to measure it, right? Makes sense. So what you do then with your experiment is after everything is completely done, you kind of tap the eudiometer on the table to get all the bubbles that kind of stick on the side of the eudiometer out of there. And then the first thing you do is you plug the hole and then you set the water level in the tube equal to water level in a container outside. So oftentimes I use a really big graduated cylinder to make that happen. And the reason why we do that is if I make the water level in my eudiometer equal to the water level outside the eudiometer, what I've done is I've made sure that the pressure inside the tube is equal to the pressure outside the tube. Because what you'll see is as I move that, the water level changes because of how the air pressure is pushing up into your eudiometer. Okay? So, like I said, keep in mind, when the two levels are equal, pressure in the tube is equal to the atmospheric pressure. So what we call that pressure then, which is atmospheric pressure, is we call it a wet pressure. And we call it a wet pressure because there's water vapor that's contributing to that pressure and some hydrogen in this case. So inside this tube for that experiment, I have a mixture of probably mostly hydrogen, but a little bit of water. And if I want to figure out just the pressure of the dry gas, I need to do a little bit of subtraction. So what I'd need to do is I'd need to measure the temperature of the air and the water. They're probably going to be relatively close. I'm going to measure that pressure, and then I need to take out that pressure to get the pressure of my dry gas. I'm going to go through an example of that so that you know what I'm talking about. So there's two examples that we are going to work through. The first one is a kind of fraction-y problem. So it says 15 moles of gas combined to create a pressure of 752 millimeters of mercury in the container above. So you can see up here, I have oxygen and nitrogen and 15 moles of them combined to give me this pressure. How many moles of gas are contributed by the oxygen? Okay, so we're going to work through this one first. If you want to pause this, we're going to go through them now. So if you want to pause this, you can. We're going to work through this together and I'll get my dot cam out and then we'll kind of see how things go. Okay, so pause it, start it, whatever you got to do. Okay, so if I take a look at this problem, I have my 15 moles of gas and then I'm only given the pressure, but I don't know how many moles of each of them I have. However, what is important is I know the pressures of each of these individually, and that's going to be super critical here. So what I'm going to do is if I know that my total pressure is 752 millimeters of mercury, Oops, you can't see that. Hold on. And my pressure of my oxygen is 159 millimeters of mercury. Okay, so I've got my two pressures here. What I am able to do is I am able to set up and create that mole fraction that we talked about. So what I can do is I can set that ratio up and figure out what essentially percentage of my pressure is coming from oxygen. So I am going to do that ratio. I'm going to take 159 millimeters of mercury, and I am going to divide that by my total pressure inside my container. Okay, if you notice here, these cancel out, and then I divide those two and I get 0.211. So the pressure of oxygen is contributing a little bit more than 21% of my total pressure in my container. Now, if I know that 21% of my moles are coming from oxygen and I had 15 moles of O2, then I can figure out my total moles of oxygen. Oops, I'm sorry, moles total. Moles of O2 are going to be 3.17 moles. Okay, so that is one way I can use my partial pressure. Okay, the second question then, let me get back here. Is about vapor pressure. So it says 85 milliliters of oxygen are collected over water with a temperature of 25 degrees Celsius. The total pressure of the gases is 55.8 kilopascals. What is the partial pressure of the dry gas? So this is one of those things where you can't just know the vapor pressure of water off the top of your head. You would need a chart, or they would need to tell you that. So if we go back and look, 25 degrees, the vapor pressure is 23.8. And this is in millimeters of mercury. So I'm just going to make a little note of that as I go along. We'll go back to our problem. Okay, so total pressure is 55.8, and we're curious what the partial pressure is. Sounds good to me. So if I go, that's my vapor pressure. Okay, we talked about how total pressure of a wet gas is equal to the pressure of the water vapor plus the pressure of whatever gas is going to be in there. Okay, so in our case of our problem, if I go back here, we have oxygen and the total pressure is 55.8 kPa. Okay, and we know our vapor pressure is 23.8 millimeters of mercury. Now, problem. These two things need to be in the same units so that I can do a little bit of subtraction to get the pressure of the gas that I am looking for. So I am going to convert that into kilopascals. And so I have 23.8 millimeters of mercury. And then it is 760 millimeters of mercury for every 101.3 kilopascals. So just make sure that they're in the same units, especially if we're doing a lab, because they sometimes cause problems. So that, when we figure that out, comes out to be 3.17 kilopascals. Okay, so what I need to do then is I'm going to rewrite my equation. 55.8 kilopascals is equal to 3.1 kPas plus the pressure of my dry gas, which is oxygen. So it's just basic subtraction now. Okay, so I've got 55.8 minus the 3.17, and the pressure of my oxygen gas then is 52.63 kilopascals. So you just have to do that subtraction. So just please be aware that this is something that you are going to run into and that you should just be prepared for it. It's always coupled with some other type of law, so just be ready for it, all right? So if you don't have any questions, we should be good to go. Try your homework, give it a shot, and if you have any questions, please make sure you ask. Good luck.